Let me share my screen. So I actually have not prepared slides. I hope everybody went through the slides we have. I'm just going to basically show some of the features again on the software just to remind you, and then we can have a discussion. I mean, obviously parameter estimation is quite a deep field. We could spend the whole workshop just talking about it. Several of the projects are going to also require it, so this is certainly an important topic. So first of all, parameter estimation is a means, it's a task that we have in Copasi, as you can see in this model that I have loaded. It's this task here in the task list. And the parameter estimation is essentially a way of trying to make the model adjust parameter values such that the model can approximate the data. As you can see here in this case with in two different experiments, we're just have in this case one variable and several experiments, and we're trying to fit it. And the blue line, the solid line is the model, and the crosses are the actual experimental data. And essentially what the parameter estimation is trying to minimize that distance. And of course you do that by allowing the model to change values of some parameters. In this case, they have a very simple model loaded here. It's actually a model of just a Michaelis-Menten reaction and some data that was generated supposedly by absorbance. It's actually simulated data, but it's the same. And several experiments were carried out. So a couple of things to bear in mind here. When you do parameter estimation, you need a number of things. So first of all, you need to identify in your model what are the parameters that you allow, that you want to fit, which parameters you don't have good estimates for. That's one thing. And the second thing is you need to identify what is the nature of your data? What are the variables that were measured in the real system, in the experiment, and associate that with variables of the model. And it turns out that you may have done experiments in different conditions. So then it's also necessary to express the conditions very precisely. Okay, so I'm going to show you what the data from this model that I'm fitting here, what it looks like. Give me a second here because I need to load the actual data file. So this is the data file, and I'm going to make it a little bigger so you can read. In this case, it's a tab delimited file, so these are tabs in between the data, and I have three columns. I do actually have a line that has a legend. This is always useful so that you can remember what the columns are, particularly if you have a lot of columns and they're labeled. So in this case, the first column is the initial concentration of substrate. The second column is time, and the third column is absorbance. And if you notice what we're plotting absorbance versus time. So this first column here, the initial concentration of substrate, you will see in a moment, it's going to be required to specify the experimental conditions, which are different in each of the experiments. So let me just scroll down through the file. You can see it's a long file, there's a lot of data. There is an empty line here between this one and that one. And if you see the time ended in 30 in that one, and it starts in 0.03 in the next one. So this is actually the end of one experiment, and here starts another experiment. So my file can have several experiments. And in this case, it does have several experiments, one there, another one here. As you can see, they have different concentrations of the initial substrate and so forth. So there's many different experiments contained in this data file, but that's basically it. This is just the data that was passed to the model. And in Copasi, that is in this page, this is the parameter estimation page. There are three regions here that are important. One is this top part, which is the definition of the problem. And then there's the bottom part, which is the how to solve the problem, the algorithm we're going to use. And there's a third one, which is actually the experimental data. And here I'm showing you how the experimental data is defined. So there is a file here that that is the file I actually am showing here on the side, is the same file. And it contains several experiments. Copazzi detected several experiments because of that empty line that I left between them, and just named them in a sequential way, essentially. Of course, you can change the names if you want to change the names of experiment. The names are whatever you want them to be, but obviously you want some things that are descriptive. Now, the other thing that Copazzi needs to know is what each of the columns mean for the model. So the second column, let's go to that one first, that's time. And because we're fitting a time course, then that we have to tell Copazzi that that's a special type of variable, which is time. And in fact, Copazzi would have detected it all automatically because the word is time. The second one, we need to say this absorbance column is a dependent variable in our model. So it's a variable of the model. It's not a parameter. This is what we measure. This is what we're trying to fit. And so we have to select it as a type dependent. So all the dependent variables are the variables that are the things that were measured and are the things that we want to match in the model. And so we have to actually choose in the model what that is. In this case, it's a global quantity defined in the model. And then the final one is that first column that I told you, it's the concentration of the substrate, which is a parameter, right? The concentration of the substrate at time 0 is a constant. It's not a variable. Concentration of substrate a long time after time 0, that is a variable, but not the concentration at time 0. That's what we have constructed in our experiment, such that it's actually different in different experiments. So we manipulated that initial concentration by diluting the substrate to different concentrations. So we have to tell Copazzi that this is what specifies the conditions of the model, and that is an independent variable. It's a parameter, and we defined it to be the initial concentration of the substrate, which you do by going here and selecting initial concentrations in the species and then choosing the right one. So that is defined for the first experiment. And then we also ticked here in this model that we also want to copy the definition to the next experiment, and then the next experiment copies to the next. So they all have the same structure. They didn't have to, but it's actually useful to have one file that you have the same structure in the file. Otherwise, you're going to get confused by it. Don't believe me. Even though Copazzi could deal with it, you might have a lot of trouble defining everything. So it's one file, contains 5 experiments. And having done that, I've specified my data, what I want to change in the model to allow fitting. And then here I just have to select one algorithm of one of several optimization algorithms to try and solve my problem. So once you do that, you can then just run, let's use evolutionary programming, which is what Aurélie used in her studies, if I read correctly her slides, and we can run this. Now I'm also plotting here the progress of fit that shows us the sum of squares, which is going down in a logarithmic scale, and so eventually this will get a result, maybe not the best, but then we can follow it with another algorithm and try and refine the solution. So this is what the algorithm did. So it's not really a very good fit, as you can see. This doesn't fit the data very well, nor does that. And so you can see that it's actually not a very good fit at the moment. This is probably the only one that's kind of okay. So you can see lots of the others are not very good fits at all. So what we can do is continue the fit from here and apply another algorithm, in this case, a local optimization algorithm, to refine the solution and see if this is going to help us. It didn't actually. So we try a different one. And that also is in the local minimum, the algorithm. So essentially what we want to do is to choose a different algorithm and see if we can then do better with that. So I'm going to choose the particle swarm. It's a very useful algorithm. But these global optimization algorithms, they like to start from random parameter variables, random starting position. So I'm going to randomize these numbers because we are currently in a local minimum, and randomizing them allows the algorithm then to find an optimal. So there it is, and it's found something better already, because if you remember, the other one was at 100, this one is close to 10. So as you can see, now I have a much better fit. Let's look at each one of them, and it's still not perfect, as you can see here. This is not a perfect fit for that variable. This one is okay, that one is okay, and so are all the others. So one of the experiments is not very well fit, the one with the lowest concentration, and that's because it's not matching the initial, the offset there. So we can refine, as I said, we can continue from this and try and get a better solution, and maybe a little better even. And we can continue. Eventually it will fit as best as it can. I think this is the best so far. It's not perfect, but it's the best that we could do so far. So anyway, I'm going to stop here. You all saw the videos, hopefully, so you must have lots of questions about parameter estimation. One thing that I should mention was a question in one of the videos, was that whether if we should run parameter estimation several times and then take the average. And the answer is no, you don't want to take the average. You want to run and you want to pick the one that has the lowest sum of squares. So whenever you look at the results, you want the one that has the smallest value of the objective function, not the average, the smallest, because that's the best fit that you obtained. Okay, you may want to run several times, but then you want to pick the one that has the smallest value, not do an average about them. But anyway, so I'm going to open this up for questions. And hopefully we can address them, your questions, and maybe with the example as well.
I have a quick thing.
Yes.
So is the experimental data that you put in, it's like 1 point per time point? What if you had like 4 trials? Could you enter all of those values?
Exactly, yes. So that's a very good question. If you have replicates, what do you do with the replicates? And some people prefer to get an average value and only plot the average value, but it's actually better to have replicates. I'm trying to think if I have here a case where I have replicates to quickly show you. I don't have one that I can go quickly, but essentially you would just add, in your data file, you would add several experiments. Let me show that again. So you would add, let's say you repeated this experiment, right? And you have another trace. So you can add that as a second experiment. It just has the same substrate concentration. And then it has different values of absorbance because, of course, it was a second one. And then what Copasi will do is that it will try to fit all of them. And if you have 4 of them, of course, it will actually fit what would be the average value or what would be the median value, really, because if you have 3 of them that are very close, but the third one is an outlier, it actually will get much closer to those 3 that are similar. And so the question normally is, should you use all experiments or do an average value? And the answer is all experiments is always better. The more data, you will always have better results.
It's to some degree quite obvious. If you have 4 values to fit, you have 4 times the information. If you just have the average, there's just 1 information.
Yeah.
So it would take distribution and all that into account if you give it 4 versus just giving 1 the average.
Exactly.
Gotcha.
So does that answer the question?
Yeah, it does perfectly. Thank you.
Okay. Any other questions?
Yeah, I had a quick question, Pedro. At what point can you be sure that your objective value is good enough?
Well, a short answer is that there's many criteria that statisticians have developed. I really like the one that says you should look at the data, and here it's obvious what is wrong with this fit. It's actually overestimating the data everywhere, even though this is probably a minimum, a local minimum here. Here you can see that the curve is actually underestimating the data. It's underfitting. Most of the error is, most of the points are above the line. This one is very good, right? All the points are scattered around the line, and it's really a very good fit. So visually, it's very important to have a visual inspection of your data. Now, that's not to say that that's the best way, because I mean, you cannot by eye distinguish between a fit that has an objective value of 13 and one that has an objective value of 12.5. You really need to look at the number here. This is you know, the weighted sum of squares. But this number, of course, it's dependent on your data and on your system. The number 13 there's nothing particular about it. In many other parameter estimations, I have numbers like 10,000 or 10 to the minus 3. That value itself is only dependent on the actual data that you have, the values on the y-axis, how many data points you have. And different systems have different values, so that you will need to run 1 or 2 parameter estimations before you find out what is a number that is low here, if you just want to guide yourself by the objective value.
Maybe one thing to add to judge, we also can plot the error. It will just show the experiment and the fitted value, but if you plot the error and look at the error and that looks like a random cloud, then you're good.
Okay, so let me show you how you would do that. So you actually come here to parameter estimation, you click output assistant, and you can just do plot of parameter estimation result. This is going to do one similar to that one, but and so I'm going to show you another thing, which is now that I have a fit, I just want to plot it again. So I choose an algorithm called current solution statistics, which basically doesn't run any optimization, just plots things as they are. So I run that. I've got a new plot. Now this plot I have also includes the weighted errors. So I just switch off everything else, and I'll have the distribution of my weighted error. So these are all the residuals. Each data point here is the difference between the line and the corresponding data point, okay, for the 5 experiments. And in fact, I can show it per experiment. So you will see that, for example, for this experiment, they are quite scattered around 0. 0 is here. So you have a good fit. The distribution looks random. And okay, it's less error at the beginning, but then also the values are smaller. So that's why there is less error. But the error is scattered around 0 equally, right? So there's no real pattern. And I can go to the others. This also still looks okay. This one's starting to have more values below the line. So now you know that there is some bias in this experiment 2. So you can also plot experiment 2 and look at it. That this is reflecting the fact that most of the data points are above the line. So it's not a perfect fit, but I think anyone would be happy with this, with real data in parameter estimation. You would be very happy with this fit already. That one is a different story because it's all above 0. That doesn't even go below. And you kind of see a little bit of a curve here. It seems like it's kind of going up. And that's that particular one that's not as good. Right, so that's showing you in the residuals that this is not a good fit. There are other things you can look at in the results. So the main page shows you the objective value and some other statistics like the root mean square. So that's that value divided by the number of data points. The square root of this value divided by the number of data points. That actually is the average distance between the lines and the points, the model and the data. But you can look at the parameter values, how they were estimated. And if you have good enough data, if you have sufficient data, the Copasi can also show you coefficient of variation.
There
So,
you see something else. You see the red, Pedro?
yes, yes.
Maybe we should talk about
what the issue is, yeah. But I'll get there in a second. So you have your parameters that you're trying to estimate, and it shows you the value that they estimated and the coefficient of variation. So this is plus or minus 9%, let's say, the coefficient of variation. That's the standard deviation divided by the mean. So that's actually pretty decent. These are good estimates. However, as you can see in the offsets, which you're also trying to fit, their values are very close to the limit. So 0.02 is actually your upper bound. So the estimate is really against the upper bound. That's why these are pink or red. And this one is pink on the lower bound. So really these offsets are probably not good enough. They're probably too small or too large for the fitting, and maybe you want to constrain it a little more or not. But again, if you look at the coefficient of variation, these parameters now have a larger coefficient of variation, so you know that they're probably what's the source of the problem. So you could look at these parameters, which are here, the offsets, and you could think about maybe not having them as large. That could, because you see what happens here is that or having them larger, because of course you can see this first data point is below minus 0.02, which is really the lower bound of this. So we want to expand it. In this case, we want to say, okay, it can go to minus 0.04. And let's see if this would work better. And as you can see, the fit improved considerably already. And maybe that was not enough. Maybe I have to make it even lower, and now I have a very good fit. Okay, so this is an important index to find out what the problem is. And by the way, I know it's a very good fit just by looking at it visually, but you could see now in the parameter values, you can see that the coefficient of variation for that offset is now small, and it's smaller than the others, because the others I'm not letting them also, I didn't change them. If I was to change them to a larger value on the upper bound, I now have very good fits all around. And if I look at the coefficients of variation, even though they're hitting the maximum, the coefficients of variation are now much lower, as you can see here. So this is another way of trying to look at the quality of the fit. This is by parameter. This may give you hints on because of course, for each parameter, you tell it, oh, it can change from this value to that value. If you give it too small a range, then it will hit the boundary and it won't improve from there. I see there are two hands raised, so maybe Roma first.
I have a few questions. So the first one, for example, if my model can show 6 species, but in experiment, I have only 1 species, which is actually a sum of these 6 species. Can I fit the data in this case?
Yes, you can. You can do that. I mean, so first things to start with, let's discuss one issue, which if you have 6 variables and you only have as measurement the sum of them, the fit is not going to do miracles, right? You only have the sum, and there's many ways in which the sum can get to a certain value. So you have less information than if you have measured the 6 things independently, but you can definitely fit. So what you would do is that you would create a global quantity that sums the species. In this case, I only have 2 in this model, so I'm going to create one that sums 2 of them.
Yeah, but
you create a new quantity. You just call it whatever you want. In this case, I'm going to call it sum. And then you say that it's an assignment. And now you add the variables that are included in that sum. So in this case, I would have the concentrations of 2 species here, S and ES. So choose one, and I'm going to add that to and pick the other. So in this case, now I have a new variable called sum, which is the sum of two species. So then in your parameter and then in your data, this is not going to work because what I have is not the sum of the two, obviously, but I'm just showing you what you would do. Then in the experimental data here, whatever you're measuring, you pick wherever the column that has that sum measured, you would pick the global quantity that you created, and you would then fit that. So now you're fitting the sum of 6 things. But as I said, it's not going to do miracles, right? You have 6 variables, you're only measuring the sum of them, so you're still leaving a lot of degrees of freedom that there are no measurements for. So you can certainly fit that, but most likely that fit will not be unique. You may have different combinations of parameter values that will fit equally well.
Yeah.
Okay,
in this example Pedro showed, we actually didn't measure the substrates, we actually measured the absorbance. And we fit the absorbance, which is a function of the concentration.
Yeah, that's true, but this was not sum, so I answered directly to the sum.
Yeah.
Thank you. And the second question, so I saw in the previous lecture that the optimization methods can search either global minima or local minima. And what is the better way to optimize, to make a parameter estimation? Is it to use only methods for global quantity, global minimums?
So that's a very good question. So I'm going to show you an example again. I'm going to randomize the data. So the initial conditions are now random. So if I show you what the current fit is, it's very poor. In fact, the residuals would show this better. So you can see the residuals actually reflect the data. So this is a terrible fit. And what I do is, the best way to do this is you start with the global optimization algorithm. But you do one thing, you tick up this update model, which means that when Copasi finishes, the values of parameters that it fits, it puts it back in the model and they become the initial conditions for the next run. So I would start with the global algorithm. For example, let me pick a different one than we had before. For example, the genetic algorithm. And I want to run it a bit longer than that. You can change the settings there. Then you run it. You wait for it to work a little bit. It came down to some value, and the fit is already not bad, right? As you can see from the data here, it's already looks like a good fit. But then from here, even if it's already looks like a good fit, let me show the residuals. They're actually pretty decent, but there's still some biases. Like this has a pattern here, and it's all above 0, for example. And that one it's mostly below 0, and again, it shows a pattern. So that fit is not perfect. It's good, but it's not perfect. That means now you can use a local algorithm to try and fit it better. So because I used the update model, the values that the algorithm got for the best values for the parameters, 58 for the first one, for example, they're now here loaded already as the start. So now I just change the algorithm and choose a local optimization algorithm, for example, Levenberg-Marquardt, and run it from there. And as you see, the sum of squares went from 16 to 13 or 12.8. So now there is a much better fit. And again, if you look at all of the data, now there's still some patterns there, but they're much less pronounced, and you have a better fit. So that's usually what we normally do. We run a global optimization algorithm first, and then after that, we follow up with one of the locals. The locals are Marquardt, Hook and Jeeves are probably the 2 best local algorithms. Praxis is also not so bad. These are local. The global are all the evolutionary algorithms, differential evolution, evolution strategy, genetic algorithm, particle swarm is also particularly good. And now let me go to the next question by Theo.
It might be worth pointing out too that you uncheck the randomized start values because just as a kind of quality of life thing, sometimes you get a very good fit, and then if you don't uncheck randomized starts when you go to the local thing, it'll just re-randomize all of the values that you got from that previous fit, and you kind of start over.
Yeah, so what Joe is saying is if you run parameter estimation with Copasi, you probably got caught into this problem many times. So an easy way to randomize start a global algorithm at random is to actually click this thing here that says randomize start values. So when you do that, whenever you run an algorithm, press the run button, the first thing that happens is that these values get randomized and then the algorithm starts, right? So now I did that. I got some value that is okay. I want to run a local. I switched to local. I have the update model, so my model was updated. That's all fine. Now I choose a local algorithm. And if I forget to unclick this, it's not going to start where the previous one ended, because before it starts, it randomizes again. So I'm going to do that, and it's going to be a terrible solution. It's going to be worse than the previous because it randomized. Actually, it's not, but just by accident. But it's also didn't get better. That when you run the second time, you have to remember to get rid of this. Otherwise, every time you start it, it starts random. Of course, this would allow you also to run many times at random positions. That's something you can do. So just repeat the run button. So you got a result here. You could save this and save the results for the parameter values, and then you just run it again, and it will run another random initialization. I normally like to watch this plot because you see where you are. We've run it already once, so I know 12 was a good number. I know that 300 is a terrible number, so this is a very bad fit. I don't need to look at the data anymore to know this is a bad fit because I already got the hang of it. Okay, let's go to Theo because we might be running out of time here.
Well, thank you. Can you hear me okay?
Yes, go ahead.
It was more of a sort of slightly trivial question, but if you had, say, with the example of sort of 6 species and different experimental data, if you did one experiment where you had multiple species and it was measured over minutes, so like every minute, and another that was only every 30 seconds,
yeah,
would Copasi have any problem with the fact that there are like blanks in certain places for stuff?
No problem.
Okay,
we have
cool.
no problem with that. You would probably want to add that as 2 different experiments, though, even if it was the same, because otherwise, yeah, that's how it would how I would do it.
So you would want it as a separate experiment, not in the same column.
As separate experiments, even though they are not, but it would still fit both of them. Yeah.
Okay. Cool.
Yeah.
Thank you.